Hey, welcome! Today we are tackling a word that sounds way more complicated than it actually is, convolution. And look, before you get scared off by any math, just forget the formulas for a minute. The best way to think about convolution is as this amazing tool that lets us see exactly how a system, any system, changes a signal that passes through it. So let's just dive right in.
Really, this is the big question at the heart of all signal processing. I mean, think about it. You've got an input, right? Maybe it's your voice going into a microphone, and you've got a system, that's the microphone itself. So how on earth can you predict what the output, the actual recording, is going to sound like? Well, this is the exact problem that convolution was invented to solve.
So here's how we're going to break it all down. First, we'll set up the basic question. Then we'll define what convolution actually is. After that, we're going to really dig into a super intuitive way to calculate it called the sliding method. We'll also touch on a few other ways to do it, and then, the best part, we'll see why any of this actually matters in the real world.
Okay, so let's get a little more specific about our problem. We're usually talking about a special kind of system called a linear time-invariant system, or LTI for short. Now, the key thing you need to know about LTI systems is that they have a predictable fingerprint. If you can figure out how the system responds to just one tiny little blip, we call that its impulse response, you can then predict how it will react to any input you throw at it. But to do that, you need the right tool for the job.
And that tool, you guessed it, is convolution. It's basically the mathematical engine that takes your input signal, runs it through that system's unique fingerprint, the impulse response, and tells you exactly what the final output is going to be. Bottom line, if you want to know the output, you have to do convolution.
All right, so we know why we need it, but what is it? What are we actually doing when we convolve two signals? Let's get into the nitty-gritty of the definition.
When you read a definition like this, it can seem a little abstract, but let's break it down into just a few simple actions. Forget any scary-looking math for a second. All convolution is, at its core, is a repeating process. You reverse one of your signals, you shift it, you multiply the parts that overlap, and then you add up the results. That's it. Reverse, shift, multiply, sum. That's the whole game.
And this is what it looks like when you write it down. Now be careful, that little asterisk isn't multiplication, it's the special symbol for convolution. It's pretty cool, right? This one little equation tells us that our output, y of n, is what you get when you convolve the input x of n with the system's impulse response h of n. It packs that entire process of reversing, shifting, multiplying, and summing into one neat little package.
Now for the really fun part. How do we actually do this? Well, there are a couple of ways, but my absolute favorite, and the one that makes the most sense visually, is called the sliding method. This is where that abstract definition becomes a really concrete step-by-step thing you can actually see.
The process is exactly what it sounds like. First, you take one of your signals, it's usually easiest to pick h of n, and you flip it, you reverse it. Then you line it up with your other signal, x of n, so their starting points match. You multiply the values right where they overlap and add them up. That gives you your first output point. Then, you just slide the reverse signal over one spot and do it all again. And again, and again. Let's try it.
Okay, so let's say our input signal is the sequence 1, 2, 3, 4, and our impulse response is 1, 2, 1. Step 1, we reverse the impulse response. In this case, it actually stays 1, 2, 1. Now, we line them up at their starting points. With the origins aligned, only the first numbers overlap, so we multiply them. 1 times 1 is 1. Since nothing else is overlapping, the rest is just 0. So our very first output value, y of 0, is just 1. Easy, right?
Okay, what's next? We slide our reversed signal one step to the right. Now look at what's overlapping. The 1 from our input is lined up with the 2 from the impulse response, and the input 2 is lined up with the 1. So we multiply those pairs and then add them together. We get 1 times 2 plus 2 times 1, which is 4. And there you go, that's our second output value. You just keep doing this, slide, multiply, sum, over and over, until the signals don't overlap anymore.
And here's a super useful trick. You can actually know exactly how long your output signal is going to be before you even start calculating. The formula is just the length of your first signal plus the length of your second signal minus 1. So for our example, our input had 4 points, and the impulse response had 3. So 4 plus 3 is 7, minus 1 is 6. That tells us our final answer is going to have exactly 6 points. It's a fantastic little sanity check to make sure you're on the right track.
This quote gets at something really important. If you were to shift where your input signals start, what we call the origin, the actual numbers in your output would stay exactly the same. They'd just be shifted over too. So the shape of the output is determined by the signals themselves, but its placement in time, well, that's all about where the inputs begin.
So the sliding method is awesome for really understanding what's going on, but there are faster ways to do this, especially if you're a computer. And it's also really important to know about a common mistake you can make if you're not careful.
Let's just quickly look at the main methods out there. We've got the sliding method down, and that is, for sure, the best for building your intuition. Then there's the tabulation method, which uses a matrix. It's really fast for calculating, but it can be easy to lose track of where your signal is supposed to start. And finally, there's something called circular convolution, which is used a lot in digital processing, but it comes with a big warning label we need to talk about.
So everything we've been doing so far is what's called linear convolution. Circular convolution is a different flavor where the signals are treated like they're wrapped around in a circle. The big danger here is something called warping. If you're not careful, the end of your output signal can actually wrap around and mess up the beginning. The fix? Well, you have to add a bunch of zeros, we call it zero padding, to both signals until they're as long as the final output we calculated earlier. That stops the wraparound effect and makes the circular method give you the exact same result as the linear one.
Okay, so we've been deep in the math, but why should you actually care about any of this? Because this one single operation is running silently in the background of so much of the technology we use every single day. Just think about it for a second. When your phone's camera sharpens a photo, that's convolution at work. When a musician adds that big, echoey reverb to a song, they are literally convolving the audio with the impulse response of a space like a giant concert hall. When a doctor looks at an EKG to check your heart, convolution is being used to filter out noise and find important patterns. It is everywhere, filtering, analyzing, and shaping the signals that make up our world.
So the next time you use a photo filter or hear a cool sound effect in a movie, just take a second. You're not just seeing an effect, you're seeing the output of a system. You're seeing the elegant result of a simple process: reversing, shifting, multiplying, and summing. You are literally seeing convolution in action. So my question to you is, what else around you works this way? Thanks so much for joining me.